We're going to start with a quick review of entropy because this plays a role in Gibbs free energy. Entropy is a measure of the possible arrangements that a chemical can occupy. The more possible arrangements, the higher the entropy. All chemicals have a positive entropy value. In chemical reactions and physical changes, we can determine the change in entropy based on what happens to the particles. So a positive change in entropy, positive delta S, is an increase in entropy where we have more arrangements of our particles. A negative delta S is a decrease in entropy where we have less arrangements for our particles. We can increase entropy in a number of ways. When going from solid to liquid to gas, changing states of matter, we increase our entropy as the particles have more freedom to move. We increase entropy when solutions form from solids by dissolving them because the particles separate from each other and again can occupy more arrangements. Entropy also increases when the number of gas molecules increases in a chemical reaction. So comparing reactants to products, when we see more moles of gas on the product side, that is an increase in entropy. If we do the opposite of any of these, that would be a decrease in entropy and a negative entropy value. Entropy calculations. Entropy can be calculated using standard molar entropy values from a data table. This is just like the calculation for delta H of a reaction. You can see the equations that we have here are very similar, where we take when we did enthalpy, we took the enthalpy of formation of our products minus the enthalpy of formation of our reactants. We multiplied by the number of moles in the balanced equation and found our total enthalpy of reaction. Delta S is the same process, products minus reactants, and we're going to get the values from a table. The biggest difference between the two is that in our table for the enthalpy of formation, delta H, we had values that were 0 for chemicals in their elemental form. For instance, we saw oxygen gas a lot. Oxygen gas doesn't need energy to form, doesn't have an enthalpy value because it's already formed. It comes that way in nature. Delta S, however, has a value for every chemical. So we need to make sure that we are incorporating all chemicals and bringing those values from that table. The table will be found in the back of your book and we'll reference it in class for page numbers. Now we are going to take a look at Gibbs free energy. We start with entropy and enthalpy because both of those actually play a role in Gibbs free energy. So we will be using those to help us calculate as well here. So what is Gibbs free energy? The change in Gibbs free energy for a chemical or physical process is a measure of what is called thermodynamic favorability. When a reaction is favorable, it produces free energy, which is energy that is available to do work. Work is the ability to move something against a force. So let's take an example. We put gasoline in our cars. Gasoline is a chemical. It goes through a combustion reaction in a combustion engine. And when that happens, it has energy that we can use to push against the pistons in the engine and cause that car to move forward through the engine's processes. So some of the energy when we burn that fossil fuel, when we burn that gasoline, some of the energy goes into actually pushing the piston and doing the work to create the energy and move the car forward. However, there is also energy lost to the surroundings, be it the car or the air around it, as heat energy. We also have some of the energy converted into entropy, where it is increasing because the particles are becoming more spread out, all of that. So Gibbs free energy takes all of the factors that are involved, our enthalpy, our entropy, and the temperature change, and puts it into one value. If that value is a certain sign, positive, in this case negative actually for Gibbs free energy, then it is a favorable process. It produces energy that we can actually use to do work, to power a car or perform a task. So Gibbs free energy helps us figure that out. Can we actually utilize the reaction to do something with it, with that energy? So Gibbs free energy is symbolized by delta G with a little zero not symbol. So a standard and Gibbs free energy, and is a measure of, or measured in kilojoules per mole reaction, just like delta H is measured in kilojoules per mole, because it is still an energy value. So a little more about Gibbs free energy. It can be used to determine if a chemical system is favorable based on the value we calculate. So a favorable system is the one that will occur without any outside energy source. We also sometimes call this a spontaneous reaction. So it will occur on its own. This does not necessarily mean it's a fast reaction, but that it doesn't need us to have any influence for it to actually happen. So it can happen out in nature, and it is a naturally occurring process. Okay, it's a favorable process. We have all kinds of favorable processes happening, say in our bodies, our biological systems. The chemical reactions they go through are favorable because they occur on their own without outside influence. We're not forcing them to happen. So as I've said, we can determine if a system is favorable by looking at the sign of our delta G value that we calculate. If it is less than 0, so it's a negative value, the reaction is said to be thermodynamically favorable, and that is the preferred term used in AP chemistry. And this is why we didn't necessarily look at our stuff in our book, because sometimes books don't use that term, they use other terms. So a reaction is thermodynamically favorable. We'll have that free energy for us to utilize if we have a negative delta G value. So it is, when we can imagine if our system has a negative value, that means it's giving off that energy, and that's the energy we can then utilize. If delta G is greater than 0 or a positive value, the reaction is not favorable and would need an outside energy source to occur. So it would need to take in energy in order for that reaction to actually happen. So it is not a favorable reaction. It does not occur on its own. If delta G is 0 or nearly 0, it says that the reaction is at equilibrium. So it's not favorable, it's not unfavorable, it just is at 0. Okay? When a favorable reaction is reversed, if we were to flip the reaction, it would flip our sign. So it would become not favorable. Just like when we did delta H and we flipped the reactions and flipped the sign, we have the same effect here. So how do we calculate? There are two ways to actually find Gibbs free energy. The first one is using standard Gibbs free energy values. This is in your book and it is referenced in class. The table we'll be using. It's the same table we used for our entropy delta S values and our delta H values. It's just a different column with different units. So this is the same process as actually finding delta H and delta S. You'll see this equation is very similar to the previous ones mentioned at the beginning of the notes. So delta G naught, the standard Gibbs free energy, is equal to the sum of the Gibbs free energy of the products minus the sum of the Gibbs free energy of the reactants. So we are going to do that same process to find our delta G values. The other equation that's given here, and all of these equations are given on your equation sheet. It would be a good idea to take a look at it and find them, get comfortable with where to reference them. This one is used more often and relates pretty much everything we've done in this unit together. So our Gibbs free energy is equal to our enthalpy, our change in enthalpy, minus the temperature times the change in entropy. So we are incorporating all of our changes in energy into one value. So enthalpy minus our temperature times our entropy. All of those pieces together create Gibbs free energy. Remember, if our delta G value that we calculate is negative, that tells us that is a thermodynamically favorable process. All right, so we are going to look at an example here. So what is the standard change in Gibbs free energy delta G for the reaction? So we're given a reaction here. Since we're not given any values for H or S, this means we're going to use our values from the back of our book in that table. So you might want to grab your book so you can check out what these values are and try this first one out. We're going to set this up just like we would the other equations that we've used. So we're going to be using our delta G naught of the reaction. So these do have that little circle naught symbol, meaning that all the values are measured under standard conditions or the same conditions. And then we want to do products minus reactants. So 2 times our CCl4, carbon tetrachloride, plus 6 times our HCl, hydrochloric acid, minus the C2H6, we only have one of those, and that is our ethane gas, plus 7 chlorines. Got that diatomic chlorine there. So then we would want to replace each chemical with its value from the table. So in the table, you're going to be taking the values out of the second column, so be careful there. When I first did this, I used all the wrong numbers, so I had to fix it. So be careful there. So maybe pause and try finding all your numbers and entering them and maybe come back. All right, so here's what we get. So from our table, the CCl4 is negative 64.0. All the units you can see at the top of the column in the table are kilojoules per mole. We're going to add that 6 times the HCl value, so negative 95.25, or excuse me, 27. And then we're going to subtract our value for the C2H6, negative 32.98. And then you'll notice that our chlorine has a value of 0. So just like our delta H, how can I put this? If the value for the chemical, or if the chemical is in its elemental form, just like with delta H, it's going to have a free energy of 0. So that chemical is already made. It appears in nature that way. So it would have no free energy because we're not creating it or breaking it down. It's already there. So then we would want to do some multiplying and simplify this down a little bit. So our left term becomes negative 699.62 kilojoules per mole. We're subtracting the negative 32.98, so we would end up adding that, and we end up with negative 666.7 kilojoules per mole. We end up with 1 decimal point because we've got 1 decimal point in that first value, the negative 64.0. Our units are in kilojoules per mole, just like our delta H values. So that's our basic calculation for that. Just like with delta H and delta S, if we wanted to find one of the values for the chemicals, we could be given the value for the whole reaction and backtrack that way as well. All right, our second equation is where it gets a little different. So this is, what is the change in Gibbs free energy, delta G, for the reaction at 298 Kelvin. So we're given the chemical reaction. We've got lead sulfide plus oxygen, giving lead oxide and sulfur dioxide. And then we're given delta H and delta S values for this reaction. So we can see that this reaction would be exothermic. It's negative 844. So it's negative, giving off that energy. And then its delta S value is negative as well. So it's becoming more ordered, or more, we're getting less arrangements of our chemicals. And we can tell that by looking at the chemicals. We're going from having a solid plus 3 moles of oxygen gas, 3 moles of gas, to forming the same amount of solid in terms of moles, but less moles of gas. We're going down to 2 moles of those SO2. So we're going from having more overall particles of gas to less. Those atoms are getting locked into place in terms of those molecules, so less arrangements. So we've got a negative entropy. Now, if we want to solve this using these values, we're going to use this equation. So delta G naught of our reaction equals our change in enthalpy, delta H, minus our temperature times delta S. Okay. So this again is on your equation sheet. You wouldn't have to memorize this, but we've got to be careful using it. So we can plug in our values. We have our delta H, our delta S, and then our temperature is given in the question. So we got negative 844 kilojoules per mole minus 298 Kelvin times negative 165. Now, here's the tricky part. Not so tricky, but we have to take it into account. The delta S value is in joules per mole Kelvin, not kilojoules. So we need to do a little conversion. So I attached that onto the end, that we have 1,000 joules in a kilojoule, so that our joules would cancel. And you can just always attach that onto your calculation. We would need to do that every time, so that we get those proper units there. So the first thing that's going to do, if we just adjust that delta S value, makes it negative 0.165 kilojoules per mole Kelvin. Now, when we multiply the temperature times the delta S value, the Kelvin will cancel. So we can see, let's take a look at some of our canceling here. So these joules will cancel there. So we've got the kilojoules per mole Kelvin. And then when we multiply our temperature and our delta S, our Kelvins cancel. So then we're left with kilojoules per mole for both terms, so that we can actually subtract them. If we want to add or subtract things, we need to have the same units for that to work. So when we do that, we would be able to simplify this down and get our final answer of negative 795 kilojoules per mole. I want you to pause right now and make sure that when you put this in your calculator, you are getting the same answer. Okay, this is most often the time when students enter this in wrong and get the wrong answer. These parentheses that we have at the beginning and the end, so that this term is actually calculated properly before it's subtracted, is really, really key to this calculation, okay? You need to have those parentheses in there so that this part gets calculated right. So pause and check that out. All right, the last part of this is we are going to take a look at the relationship between delta H and delta S. We can see from our last two examples that both of our calculations for delta G gave us negative values. So both of those were favorable reactions. We have the ability, though, to take a look at the signs for delta H and delta S and how they would influence that equation to determine when things are going to be favorable or not. So this table kind of sets that relationship up for us. So we're going to start with this first box here. So I'm going to put a little line in the corner of this one right here. So we're looking at positive delta H and positive delta S. It says this is thermodynamically favorable. So what does this mean? It means energy is going in because we have a positive delta H. We also have a positive delta S, meaning we are getting more disordered or more arrangements of our particles. Actually, I want you to put that next to it. Write that it is arrangements here, okay? They don't really like the term disordered, and I missed this one. Write arrangements instead. All of these ones, write arrangements. So this, okay. Now, so we have more various arrangements of our particles. So if we want delta H and delta S to be positive, we can take a look at our equation over here. If this value is positive minus our delta S, which is positive, a positive minus a positive tends to give us a positive value, and that would not be favorable. So what we need is this second term, the T delta S, we would need that to be big enough that when we subtract, we're going to get a negative number. And to do that, our temperature needs to be big. So for this to be favorable, we have to have a high temperature. Okay, so we're kind of analyzing, okay, what's going on with the sign of each of these values and how is that going to influence delta G? Remember, our goal is for delta G to be negative. We want that. All right, let me erase a couple of these things. We can start over. Okay, now we're going to move across to this box over here. So on the right side. So we're still going to have delta S and delta H, or excuse me, delta S is still going to be positive. So we're still having more arrangements, but our energy is being released. We have a negative delta H. Oops, wrong color. Being released here. Energy is going out. So if we look at our equation up here, we're going to have a negative there, minus. We're going to have our temperature times the delta S, that is positive. So if we have a negative minus something else, minus another number, it's going to become more negative. So no matter what, our delta G value is going to be negative. It's always going to be negative. So this works at any temperature. Okay, if delta H is negative, delta S is positive, it will always be favorable. Okay, and again, we can kind of put those negatives in and the positives into our equation and see what might pop out on the other side. So negative minus something positive is going to give us another negative. All right, let me erase again those pieces. All right, now we're going to go down to the second row here. So let's do highlighting. We're going to look at the never favorable down here. So we can't, when we look at this equation, to have something not ever be favorable, we have a negative delta S. So I have a highlighter here. So negative delta S, and still that positive delta H. So let's put those into our equation and see what happens here. So if delta H is positive minus a negative delta S, if we're subtracting a negative, we're really adding a positive. So a positive plus a positive gives us a positive value. So delta G is always going to be positive there. It will never be favored. Okay. When we say more ordered, really we want to say less arrangements. Okay. So write that in, less arrangements. I can't really write that very well. So write in arrangements. You guys got this. So we're going to have less arrangements. We're going to have it being endothermic. So nothing here is really helping it go on its own. So we're going to have an unfavorable reaction there. All right, last box. So thermodynamically favorable. Okay. When we have a negative delta S and a negative delta H, we are going to get favorable. So energy is released. It's going out. Exothermic. We have less order to our particles. Okay, or less arrangements, not more ordered. Less arrangements. So they are becoming, they have less states that they're in. So our temperature must be low for this to occur. So let's look at our equation and see why temperature has to be low. So delta H is going to be negative, minus. Delta S is going to be negative. So when delta H is negative and we're subtracting from it, we're going down, but we're subtracting a negative, then we're really adding a positive. So when our temperature is low, so let's think about this. When our delta H is negative and we're adding something that's positive to it, that's going to start approaching a positive value. So for this to work, we need our temperature there to be pretty low, so this term, the T delta S, doesn't get too big, okay? So that we're not adding too much to our negative value. So we need temperature to be low for it to be favored, okay? So 3 out of the 4 situations can have a reaction be favored, which is why we have so many reactions out there that work. Only one of them always works at all temperatures. One, we need high temperature. One, we need low temperature. So it's kind of just some analysis. I know this looks super messy now. There's lots of resources out there on the relationship between delta H and delta S. So if you feel like you need a little more explanation, what I've given here, feel free to do some Googling, look on YouTube, look for some relationship stuff there, okay? And we can talk more about this in class too if you guys have questions, right? Thanks.